Hello everyone, my name is Nischal. My roll number is 1801 CS33. Today I'll be presenting our deep learning project on multivariate time series forecasting. This project is done with the help of my team members V Sriram, whose roll number is 1801 CS37, and Navyasree, whose roll number is 1801 CS06. The organization of this presentation is as follows. First, we'll talk about what multivariate time series forecasting is. And then we are going to talk about various different evaluation metrics which we use for evaluating the results obtained on time series. And then we are going to talk about the specific data set which we are using. And then we are also going to give details about the models which we have implemented and the results which we obtained using those models. And then we are finally going to compare different models in terms of the results obtained and the runtime and various different parameters. And finally, we are going to conclude the work. So the introduction. Time series prediction involves prediction of values of one or more variable which vary with time. So this is very popular, and we know what exactly time series is. And we also know that time series has various applications in domains like business, finance, weather, civics, and others. Like, for example, traffic prediction or temperature prediction, or let's say some kind of solar energy prediction or other things. So in time series, the data points are related to each other over the different time steps. So just to understand the difference between time series data and non-time series data, we can have a look at the tables which are provided here. On the left hand side, we can see the table of different user IDs and a given variable which is taking different values between 1 to 5. Let's say this corresponds to the clicks of a particular user on a website. So as we can see, the click of user 5 does not depend on the clicks of user 1 or user 2. So basically every row in this particular data set on the left hand side is independent of each other. So such a kind of tabular data does not qualify to be called as a time series data, because the variables, the observations of the variables are not dependent on the other observations. Whereas on the right hand side, we can see that we have timestamp where the time is sequentially increasing. And then we have a variable which again takes values from 1 to 5. So this is a time series data because the time, the observation of the variable at a later time step depends on what has occurred in the previous time step. So this is basically how a time series data looks like. So now let's understand what's the difference between a univariate and multivariate time series forecasting. So in univariate time series forecasting, we only predict one of the variable based on different time step, like the previous example where we saw where we only had one variable. But in multivariate time series forecasting, we basically predict the values of different variables, and each of the variables mutually influence each other in their observations. So here we have the differences between the univariate and multivariate time series data. So univariate only uses one variable, whereas multivariate uses multiple variables. Univariate cannot use external data, whereas multivariate can use external data. External data here means it is basically the prediction of different variables. And then univariate is based only on the time relationships, that is between the past and the present, whereas multivariate is based on the relationship between the variables with the time as well as between the other variables, which we are going to see in the further slides. So every time series problem can be decomposed into several components. So this is a technique which is used to extract multiple types of variations from the data. So the three different components of time series data are seasonality, trend, and noise. So let's have a look at the observation of time series on the right over here, and we can see that there is a time series data. It is continuously increasing with time, and it has some kind of a repetition. So here we decompose it into three components: seasonality, trend, and noise. So seasonality is basically the recurring changes occurring in the dataset over time. So here we can see that seasonality, we can see that it is increasing and suddenly decreasing and increasing and decreasing. So this is how the seasonality is happening. And trend is basically a long-term upward or downward pattern. So from the observation, we can clearly see that in the long term, the series is, the values are continuously increasing. So that's why the trend is moving upwards. And noise is basically some random changes in the data which cannot be accounted to by both the seasonality and the trend. So this is how the noise or the residual graph looks like in the case of this airline passengers data, which we can see over here. And then these are several evaluation metrics which we are using. There are certain terms. So the forecast in case of time series means the value which we have predicted from our given model for a given time step. So it's a predicted value basically, and demand is basically the true value of the time series for that time step. And there are several metrics which we are using, which are error, MAPE, MAE, MSC, and RSC, which we are going to talk about in detail in the next few slides. So error. So as the name suggests, error is basically the difference between the forecast and the demand, which is FT minus DT. One thing to note over here is that if the forecast overshoots the demand, based on this definition of error, the error will be positive. If the forecast undershoots the demand, the error will be negative basically. So this is how the error is defined. So having known the error, we can talk about more meaningful metrics which is used for time series. The first one being MAPE, which is mean absolute percentage error. So MAPE is the sum of the individual absolute errors divided by the demand, each period separately. It is the average of the percentage errors basically. So this is how MAPE looks like. So you can see that the absolute error is summed and it's divided by the demand at every time step, and it's just averaged over the n time steps. So MAPE divides each error individually by the demand. So it's quite skewed because high errors during low demand periods will significantly impact MAPE because it's going to overshoot to a very huge value. So that is one disadvantage of MAPE or one characteristic. And we also have MAE, which is a very popular metric, which is mean absolute error. So it is a mean of the absolute error, which is very simple. MAE is 1 by n times summation of absolute times of error. One issue with that is that it's not scaled to the demand value. Hence, it is common to divide MAE by the average demand, which is the percentage MAE, which is represented below in this slide. So summation over absolute value of ET divided by summation over all the values of DT. So this is a corrected MAE formula. And then we have one more very popular metric, which is mean squared error. So mean squared error is basically the sum of the squares of all the errors and the mean of it. So mean squared error is actually very popular, particularly in machine learning algorithms. So this metric is generally used for optimizing machine learning algorithms which are designed for time series data. So this is with mean squared error. We also have root mean squared error, which is defined as follows. So it's basically the square root of the average of the square of the errors divided by the total average of the demand. So these were different error metrics which we use, which we are based on which we are going to evaluate our models. So before we move to the models, first we need to discuss about the dataset which we are using. So there are many popular multivariate time series datasets. For our experiment, we are using the New York, Texas weather dataset, which is basically shows the weather in degrees Celsius of the New York and Texas, different cities in New York and Texas from 1st January 1949 to 3rd July 2021, which is very recent. And there are 6 cities which are spread across Texas and New York. So the 6 cities are based on different airports which are in Texas and New York. So the first 3, which is ABI, Abilene Regional Airport, ACT, Waco Regional Airport, AMA, Rick Husband, Amarillo International Airport, are all based in Texas. And the next 3 is Albany International Airport, John F. Kennedy International Airport, and LaGuardia Airport, which are based in New York. So we have particularly chosen this dataset because in the models part, we will show that those particular cities which belong to the same state are going to affect the weather of each other more as compared to those cities which belong to different states. So for example, let's say ALB and JFK, they both belong to New York. So any sudden change in the weather of ALB will be a premonition of a change which will happen in JFK, because both are located in New York, whereas any change in ALB may not actually imply that there'll be a change in weather or in temperature drastically in either of ABI, ACT, or AMA. So this is really important to note. So we have also implemented different models, and we have also given the results of different models. So the different models which we are implementing on NYTX dataset is a linear model, which is a very simple linear regression model, which considers the context of the previous variables. And then we have an LSTM model, which is a very popular model for processing sequential data. And we have an LSTNET model, which is the previous state-of-the-art model, which was proposed in this paper, modeling long and short-term temporal patterns with deep neural networks, which basically proposes RNN and CNN-based neural network. And finally, we have Spacetimeformer, which is the current state-of-the-art model, which is proposed in this paper, long-range transformers for dynamic spatiotemporal forecasting. So next, we are going to talk about each of these models in detail.
So talking about the linear model, in linear model we are using the linear regression model where we are using the past 128 points in order to predict the output of current point. Since it is an autoregressive linear model, the current point then becomes included in order to predict the next output. This can be represented using the equation yd equal to sum of wix I plus b, and the loss which we are using in order to optimize the model is mean square error. So the graph over here basically shows the output for a linear regression model of sales over time, whereas sales is represented vertically and time is represented horizontally. So this is the linear model which we are using, and the results are as follows. So the mean average error is 4.11, the mean square error is 28.44, root square error is 0.50, and loss is 0.27. Coming to initial epochs, here the blue points represent the context or the input data points which are required, which are needed in order to train the model, whereas the silver points represent the actual truth or the ground label of the input, and the orange represent our forecasted output from the model. In the initial epochs, there is huge difference between the ground label and the forecasted output from our model. So, whereas considering the same in the final epochs, so the difference between them got reduced, but even then, this is not much accurate as linear model is the first model used, whereas coming to next models, so this difference will be lesser. So coming to the next model, which is LSTNET. So it is the state-of-art model, which is a hybrid combination of long and short-term temporal patterns, which are using RNNs and CNNs. So RNNs are for modeling the long-term dependencies, and CNNs are for modeling the short-term dependencies. The grid which is over here is the multivariate time series data grid, whereas the vertical columns represent vertical rows represent the time, and the horizontal represent the multivariate time series variables. And we apply certain number of filters over here for the convolutional layer, and the output we get is a single dimensional array, which is then passed into a recurrent neural network and recurrent skip neural network model, then passed into a fully connected and element wise sum output, which is then used for prediction and passed into the auto-regressive model. So this is how the whole LSTNet works. And coming to hyperparameters which we have used for this model, so the GRU hidden dimension is 100, and the CNN filters are 100. CNN kernel size is 6 times the number of variables, and the dropout is zero point 0.2. And talking about the results which are obtained for this model, the MAE is 2.80, MSE 14.06, and RSE 0.35, and loss 0.13. These are the initial epochs which are obtained for this model. Even here, the blue points represents the context, and the silver points represent the truth or the ground label for the input, and the orange represented the predicted output from our model. In the initial epoch, there is a difference between the predicted and the actual output, whereas after training the model, The final epoch shows how close the forecasted output is to the ground label, and this represents that the model is very accurate compared to the previous models which we have used. And this shows that the forecast which we are getting from our model is much more accurate, and it is quite near to the ground truth value. So I'm handing it over to Sriram in order to explain LSTMs from here.
Thank you, Nischal. Now we're going to talk about another baseline model, the LSTM model. Of course, LSTM is quite popular for baseline NLP tasks because of its ability or potential to remember or forget the important parts of the sentence. Of course, sentence is a sequential item, so it is important. LSTM is able to identify which parts of the sentence are important for the upcoming words or whatever sequential task may be. So that is very much relevant in a textual based modality, but also, as you can imagine, it is very much important in a time series modality because of the factors like seasonality in time series, usually observed in time series data. So it is important, like in some parts of the previously established baseline truth, you can see that there are patterns, and LSTM will be able to identify those patterns and remember them and use them in the upcoming predictions. So that is the hypothesis that we are using to proceed with the experiment. Of course, it will be an encoder-decoder based network. Encoding will be using the baseline or the truth to predict the upcoming maybe 10 or 20 or even hundreds of steps. So that is the encoder-decoder. And of course, the teaching will be like a teacher forcing method where we'll give the actual truth to the decoder, and then in the testing it will be just using the contextual input from the encoder. So testing, only use the context vector, but training, both the parts are included in the truths. So we have mentioned some of the parameters that we have used for the training over here. Moving further, this is a basic diagram of an LSTM. So in order to get intuition why LSTM is important for this model, so you can see that there are specific layers which are meant for forgetting some part of the previous context vector, and then propagating the inputs, and and then mixing them all together and giving the right output. So this type of gate interface helps in time series modalities where it is important identify the seasonality properties of the data. Again, this is the architecture. There is an LSTM encoder and there is a decoder. And you can see that the time series steps until TX are inputted in a sequential manner, rolling. LSTM is present over here, and then there's an encoded state. You can use that state to do the further prediction until whatever layers are important. So, of course, the time series context is provided by different time steps of the encoder. That is what we have talked about. And the decoder is used to predict the outputs at every time step, right? So that is established. And again, as I mentioned earlier, we are using the teacher forcing method in order to do the whole training process. And the decoder operates in a auto-regressive manner because that is how time series predictions are done usually. After the experiments, these are the results which we have observed. It's a really good performance which has been provided by the LSTM. You can see that there's a mean-square error loss of 0.13, which is like very good. And we have pictorially also represented, like other losses are also mentioned. And Nischal has already talked about them, but you can compare the performance. So pictorially also we have represented the performance of the module. So in the initial epochs, the first few epochs, you can see that when the true state is like this, the forecast is almost horizontal, it's mostly noisy. And when there's a true state like this, the predictions are horizontal here also. But during the end of the training, you can see that it's very close to, the predictions are very close to the golden state, the golden answers or targets. So that has been the LSTM part. Thank you. Right. So we shall now talk about another implementation, another approach to deal with this particular problem statement, which is the multivariate time series graphical neural networks. Of course, graphical neural networks have become quite popular in the field of deep learning because of a few properties like permutation invariance, which is like it doesn't matter how you interchange the variables, the learning will remain the same. So there's a little bit of robustness in how you give inputs to the graph. And it is, of course, since it is modeled on a graph, it is highly permeable to local connectivity. That is the way you connect different entities, i.e., the nodes in the graph. You'll be learning different things. And of course, the graphs are highly customizable and composable, and depending on how you structure the graph, the learning will change accordingly. Now, why is this relevant to multivariate time series? Right. So the graph models are, in general, very much efficient in exploitation of interdependencies in between any of the entities in the graph. In this particular hypothesis, we consider those entities as the multivariate or the various variables which are related in a time series format. That is exactly what a multivariate time series modeling is. We were supposed to uh, extract the interdependencies or the relations between different variables in a time frame format. And therefore, graph models make sense in doing that. And of course, that is how we will try to solve it. Variables in the multivariate analysis will be considered as nodes of a graph with interlinkages and hidden dependencies. But of course, if you look at it in a straightforward manner, there are a few shortcomings that is like it's not very clear how you'll be able to model a multivariate time series data as a fixed or a predefined graph structure. So this is a time-based data, and it is depending on a various variables, which will be highly variant across timestamps. So it is very hard to put your finger on one particular graph which will be modeling it throughout all the timestamps. But then again, if you manage to do that also, it is not very apparent on how you will model it as a time series prediction problem, because usually GNNs deal with node prediction or edge prediction sort of tasks and not time series based tasks. So the way MTGNN deals with this is through three individual modules. One is the graph learning layer, which is a basic message passing layer, nothing too fancy in that. But the meat of the crux lies in the TC and the GC model, which are like the temporal convolutional model and the graph convolutional model. Now, what are these? So, graph convolutional module is something which is a convolution, is a kernel over different variables. So, it is kind of like an intervariable relationship extractor, a layer. So, in this way, each node will be able to grasp data among various variables, and that is one part of the representation. The other part is, of course, a temporal representation. So, across the timestamps, how will the data be captured? That is done by the temporal convolution model. So, we'll be using propagation layers for the GC module, and all of them will be connected through a straightforward concatenation. And for the TC module, there's an inception layer with uh, with skip gram connections and another concatenation over here. So the training of that particular model gives us these particular results, which are pretty good. Loss 0.13. Root square error is 0.35, mean square error 13.53, MAE 2.74. And we can also pictorially say this by looking at the initial epochs where the learning is very random. Here again, the orange represents the forecast, the predictions, and the gray is the actual time series data. So they're not relevant. It's very noisy in both the cases. But then after a few epochs, you can see that
the data is being quite, it's very much falling on the actual or the golden state labels. Now Nischal can take over the state-of-the-art model, which is the space-time format. Thank you.
My name is Nischal. Now we'll be discussing about the space-time format model, which is the state-of-the-art model for multivariate time series forecasting. So first, the space-time former model stands for space and time with transformer. So transformer is a popular deep learning architecture which is used commonly for natural language processing tasks. Transformer model and transformer based models have obtained state-of-the-art performance on various natural language processing tasks like summarization, classification, text generation, and others. And this transformer architecture is primarily known for its multi-head attention concept, which we are going to see in the next few slides. The proposed model, which gives state-of-the-art performance for time series data, is called Spacetimeformer, which is basically built upon the basic transformer model, but here it has certain modifications as compared to vanilla transformers. So over here we can see the actual transformer architecture over here, where basically the first thing is that we need to remember that this transformer has two parts to it. One is the encoder and the other is the decoder, because the transformer is basically trained on sequence to sequence natural language processing task, where the input is a sequence and the output is also a sequence, like for example machine translation. So having said that, we can see the diagram of transformer on the right hand side, where the encoder consists of different modules like the multi-head attention, normalization layer, the feed-forward layer, and this encoder is connected to the decoder, which again has certain multi-head attention based modules and other feed-forward neural networks. So the multi-head attention is the most important part of the transformer, and the equation of multi-head attention can be seen on the left-hand side of the slide over here, where MSA of x is the softmax of WQ of x times WK of x normalized by the dimension of the matrices and which is multiplied by the weight vectors of x. So basically the concept is that every token x will have associated with it a query vector, a key vector, and a value vector. So this multi-head attention is calculated based on this query, key, and value vectors based on the equation which is given over here. So the main advantages of transformers as compared to RNNs, including LSTMs and GRUs, is that they are faster as compared to LSTMs, as transformers can look at the entire sequence at once and do not depend on the previous tokens processing, whereas LSTMs and typical RNNs have to wait for the processing of previous tokens for processing the current token, for basically calculating the attention of the current token. And the other advantage is that multi-head attention speeds the process and gives different interpretations for the same attention value. These are the advantages of transformers, and this is one reason why transformer has become very popular in NLP or sequence-to-sequence tasks. But there are certain problems with transformers as well. The problem is that the attention computations scales quadratically with time. Hence, it is not feasible for long sequences. So as the number of sequences increases, the attention computation increases quadratically in the form of O of n square, where n is the length of the sequence. So for that reason, vanilla transformer attention mechanisms have a maximum sequence length of 500 on most powerful GPU TPUs. This works fine for NLP tasks, but when you talk about multivariate time series problems, we generally have about 23,000 length of sequences. So in this case, due to the nature of transformers, we need to make certain modifications to it. So this is where Spacetimeformer comes in. Spacetimeformer is a more sophisticated model as compared to transformer, where in addition to the stationary time embeddings, it also embeds the data with the time to vector, which captures the global time information. So when we have time series data, we have a global time information, and this global time information will help in basically predicting the seasonality of the time series data. So time to vec is one such algorithm, and the Spacetimeformer is using time to vec for doing the embeddings. And one more very important addition in Spacetimeformer is that Spacetimeformer considers both spatial and temporal variations of the data as compared to just the temporal variations. So if you see on the right hand side, we can see that since it's a multivariate time series problem, we have three different variables over here, which are represented by a triangle, circle, and a diamond shape. So what happens in general transformers or general RNNs or other deep learning models is that each of the time step is considered as a unique token, and all the variables which are correspond to a given time step are considered the same. But as we know, in a multivariate time series data, we need to find the interdependencies between different variables as such. So for that reason, the Spacetimeformer expands the variables as well, and it treats the variables separately. So that is where the spatial embeddings come into picture. So one more thing is that it also handles long sequences effectively by approximating the vanilla transformer attention mechanism from quadratic to linear using a random kernel method, which was basically published in different papers like the performer architecture. So these are the three main important additions of this thing over here. And then this slide basically represents a typical input encoding of the Spacetimeformer. There are 6 different steps over here, which is shown on the in this particular picture. In the first step, basically, this is a standard multivariate time series format. The question mark values over here, which is for T3, T4, will be inputted as 0 vectors, and they need to be given to the decoder for predicting the values. So the second one is basically the time sequence is passed through a time to wake layer to generate frequency embedding that represents periodic input patterns, which is basically required for predicting the seasonality of the time series data. And the third one is basically adding a given embedding. So given embedding can be either true or false. So basically given embedding basically specifies whether the given encoding is a context or not. If it is true, it means it's a context, which means the value need not be predicted. If it false, it means that the value needs to be predicted. So that is to do with the third one. And then we have this fourth step where we are adding the spatial embeddings. So as we discussed earlier, here we are going to treat every different variable in a given time step differently. So we are going to add a spatial embedding for every variable as shown here. And then in the fifth step, we basically, the time to wake embedding and the variable values of each time series are projected with the feed-forward neural network as shown over here, and to get the intermediate representations. And then in the last step, basically we combine everything. We take the value and time variable and the given embeddings, and these are summed and laid out such that MSA attends to the relationship across both time and variable space at the cost of a longer input sequence. So the input sequence is quite long over here because we have also expanded based on space as compared to only time. But this is beneficial as we will see in the next few slides. And also Spacetimeformer has adapted to handling long sequences. So this is a general architecture of Spacetimeformer. Here we can see on the left hand side we can see the overall architecture. It resembles the transformer architecture and some variants of transformer architecture. But here we have certain different kinds of self-attention called local self-attention and global self-attention. So local self-attention is basically used to attend to the token and the local sequence, or the basic context window in which the token is present. Whereas global self-attention is to attend to a longer global context which has already been seen by the transformer in the past. So global self-attention can mostly help in trying to handle the seasonality of the time series data, whereas local can be mostly for the noise or the trend part of it. So the norm is basically the batch norm. So this is used for stabilizing the training process. So we do the batch norm before passing it to the different layers like the attention layer and the feed-forward neural networks. And now talking about the loss functions. So the final feed-forward layer of the decoder generates a 2-dimensional vector which parameterizes the mean and standard deviation of a normal distribution. So, having said that, the normal distribution is something which looks like this. It has a mean and then it has a standard deviation, and this outputs the mean and standard deviation of the normal distribution. And we are using negative log likelihood function for optimizing the architecture. This loss maximizes the probability of the target sequence, and it makes use of the output distributions uncertainty estimates. So we'll see what uncertainty estimates are in the plots later. The model learns an intuitive prediction strategy that generally increases the uncertainty along the target sequence. So it also adds uncertainty to inflection points where temperatures are reaching daily low or high. So basically, like unlike other models, this model also has a capacity to predict something called uncertainty, which is basically the difference between its prediction and the original prediction. So this is helpful because it tells us how uncertain our current predictions are and in what bounds can we expect the actual value to be. So uncertainty part makes the Spacetimeformer unique as compared to other baseline models. So here they have introduced another task, which is node classification. So in node classification, basically given the encoder and decoder embeddings, we need to predict which variable among the different multivariables does this node belong to. So this is basically used for testing the efficacy of the spatial embeddings. So here I'm going to give a few hyperparameter details of our Spacetimeformer model. So this is the one which is reported in the paper. They are using model dimension of 200 and feed-forward dimension of 800, attention heads 8, encoder layers 2, decoder layers 2, and other such things. They for attention mechanism they are using performer architecture, which is particularly adapted for long sequences because it tries to approximate the attention calculation from quadratic to linear time using a random kernel method, and then other parameters can be seen over here. For our run, we found that these set of parameters are necessary and can be run on a single GPU because the original paper made use of 4 GPUs parallelly and was able to train the model in 4 hours of time. We were able to train it in approximately 4 hours, but we are only using 1 GPU, and we made a small change in the hyperparameters. We made the model dimension as 100 and the feed-forward dimension as 400, and we are using optimizer as Adam weighted optimizer with weight decay, and learning rate is 0.0005. So the results which we obtain are as follows for this model. So we get the mean average error as 2.34, the mean squared error is 10.50, RSC as 0.31, loss is 0.099, forecast loss is 0.098, and the classification loss, which is basically the node classification loss, which is 0.03, and node classification accuracy is 0.999. So node classification accuracy shows that the spatial embeddings are very good. And these are some plots which are there, which I am using for showing the how validation is varying with the time steps. So we can see that the forecast loss is decreasing, the class loss decreases, and then it increases after some time. We are basically optimizing the forecast loss metrics. So as soon as the forecast loss is increasing after approximately about 20,000 steps, we are doing early stopping over here. But we can see that other losses like class loss have been increasing from 5k steps as well. But since we are mainly optimizing forecast loss, we do early stopping only based on the forecast loss increase. So this is how we are getting the validation plots. And then right now I'm going to show certain results. So this is the results in the initial epoch. So in the initial epochs, we can see that the prediction, which is the orange color, is quite far from the ground truth prediction in both the plots. And here we are also getting something like uncertainty. The orange bounds which are present over here are basically the uncertainty in the predictions, which is only given by Spacetimeformer model as compared to the other baseline models. So we can see that in the final epochs, our model has learned and it is able to almost accurately predict the true values, and the forecast, which is the orange line, is very close to the true value, and also the uncertainty estimate can also be seen over here. And We have also performed one ablation study using the Spacetimeformer model. So basically in this ablation study, we are trying to remove the spatial concept and only use the temporal embeddings. So the main motivation of this is that we need to see if the spatial embeddings, which basically means that considering every variable differently, actually helps. So the results which we obtained for this temporal ablation is as follows. MAE we get as 2.71, MSC is 13.05, and RSC is 0.34. So the initial epochs are as follows. Again, like we can see that it's not well trained over here, so the predictions are quite far from the true values. But after the final epochs, the predictions are quite nearer to the true values, although not as good as the basic Spacetimeformer method. So one more thing over here is that we are going to discuss the different attention maps. In the temporal case, we are going to get an attention map as shown over here, and in the spatio-temporal phase, we are going to get an attention map as shown on the bottom right-hand side over here. So the thing is, we can see that we are working on New York, Texas weather dataset, which I'm going to show right now. So this is how the New York, Texas weather dataset looks like. There is a date and time over here, and there are different cities over here whose temperatures are varying in degree Celsius. So this is January, so the temperatures are quite low, but in New York, but they are quite high in Texas because of the weather conditions there. So having known that, let's come back over here. So here we can see that in temporal ablation only, the attention weights are more towards the previous time steps only, and they don't consider the interdependencies between different cities. But here if we see the spatio-temporal attention map, we can see that the cities which are in Texas have more attention mutually among themselves, and the cities which are in New York have more attention among themselves. So this basically means that our model is able to capture the interdependencies between different variables in the multivariate time series forecasting. So that the previous picture was taken from the paper, and this is a picture which we have got from running our own models, and we can see that for the temporal ablation map, the attention is again more towards the previous time steps. Whereas if we come to on the right hand side, we get the spatio-temporal attention map, and spatio-temporal attention map is it's more similar to on the top left hand side and more similar on the top right hand side because the spatial information is captured here, and all those on the top are basically representing Texas, and all those below are representing all those with high numbers are representing New York, and hence they have high attention weights mutually among themselves. So right now we are going to compare different models over here finally. So we have actually experimented with 5 different models and one ablation of the proposed model. So these are the results obtained. So we can see that as we come down the table, the results, the mean squared error, which is one metric we are comparing, continuously decreases, and it gives the best performance for using Spacetimeformer, which is a proposed model. And the number of parameters for every model is also mentioned over here. And Spacetimeformer has significantly higher number of models, which is a higher number of parameters, which is in millions. And Spacetime-temporal ablation model is basically having 3.4 million parameters, because I'm using a higher model size and embedding size over here, whereas I'm using lesser size for the actual proposed model because we are only running it on one GPU. So the final conclusion is that we have basically worked on multivariate time series analysis, which involves prediction of values of different mutually dependent time series variables. And then we compared the performance of various deep learning models on New York, Texas weather dataset. And then we found that the state-of-the-art model is the Spacetimeformer model, which is a special variant of the transformer architecture, because Spacetimeformer attends to both spatial and temporal information of the data and handles long sequences more effectively than vanilla transformer model. We see the importance of spatial embeddings along with the temporal using ablation studies, where we remove the spatial embeddings selectively and plot the attention maps. We obtained the state-of-the-art performance mentioned in the paper with significantly less number of parameters, which is just 1.6 million. The original parameters will be about 3.4 million, but we only experimented with a smaller version of the architecture and only used one GPU, whereas the proposed paper used 4 GPUs, and we are getting nearly the same results as was proposed in the paper. So with lesser compute power and a smaller form of the model. So this is the conclusion from my side. Thank you.